Hello, this is Harsh Singh from Team DDASH, and today we'll be discussing our problem statement for Smart India Hackathon and the solution we came up for it. So if I'll just put up the video here. So as you can see, our problem statement title is AI ML-based intelligent de-smoking and dehazing algorithm. So what we have done is essentially we have created a deep learning model and a website. So what we do is we take a hazy video, a video which is full of smoke and haze, which you can't see the characteristics of what's happening in the video clearly. We break the video down frame by frame, and then we feed it into a deep learning model, as you can see here. And a deep learning model so basically clears out all the smoke or the haze from each individual frame, and then we stitch the frame together to create a output video. We have used Python libraries such as OpenCV, PyTorch, NumPy, and stuff such as Google Colab. And we have plentiful use cases for solution as well, such as we can use this as a um, paper use service for forensic services, essentially, of our firefighting rescue operations. And business sectors we have for clients such as law enforcement agencies, insurance companies, defense departments. Um, if I'll just so yeah, as you can see in this slide over here. This is a working example of a model. We have ground the image over here, the actual reality, and then we had this input as a hazed image. So we fed this particular image into a trained model, and which produced this dehazed image. And as you can see clearly, we have recovered much more details than the input image, and we aim to do this for basically all frames of a video and basically for videos where it's not just hazy but for like smoke or fire or something like that. Mm. If So we created a website, a user-friendly website, which is locally deployed for for accessing the model, and then we have a first generation prototype ready, trained on 1600 images with a staggering accuracy of 98.1%. Now I'll have a team leader Animesh take over to explain the code and the working behind this model.
Good morning, everyone. My name is Animesh Srivastav. I'm the team leader of Team DDASH, and I will be explaining you the code of our machine learning model. So, this is our machine learning model. We are using the PyTorch framework, which is famous for its fast deep learning capacities. And this is our model, which is which I have named class D is net, which uses five convolutional layer, two refinement convolutional layer, and multiple features concatenation layers. So starting with the first convolution layer, our first convolutional layer is a convolutional layer of kernel size 1 by 1. The layer applies a 1 by 1 convolution to the input image. It helps us transform the input image by mixing its color channels while keeping the spatial dimension same. It's more like adjusting the brightness and contrast of image since it's only a 1 by 1 convolutional layer. And the second layer is a 3 by 3 convolutional layer. And by 3 by 3, I mean its kernel size is 3 by 3. And it's a much wider kernel size than the our previous one of 1 by 1. It A 3 by 3 kernel layer is basically mostly used to detect edges and textures, and the padding of our second convolutional layer ensures that the output size matches the input size. And then moving out to our third convolutional layer. Our third convolutional layer is an even wider convolutional layer than our previous one, and it captures more complex pattern and information from a wider area in the image, helping us extract more features out of the image and understanding the context of the image. And moving on to the fourth convolutional layer, which has an even wider kernel size of 7 by 7. It has the largest receptive field of our current uh, convolutional model. It can capture global context of the image and extract even more features than our three previous layer combined. Then moving on to the fifth convolutional layer, it has a kernel size of 3 by 3, and it is more of a feature refinement layer because it combines information from multiple scales and contexts. मेरे को कट करना ही पड़ेगा यहाँ से. Excuse me for the inconvenience. And the final two layers of our models are two refinement layers, which are basically to fine tune the features and to improve the quality of the final output image. Now, while the entire model, while the image goes through our entire model, during the first two convolutional layer, the features are sent as they as they are received by the second layer. But after the second layer, we concatenate the first two features and take out the single strip of features and feed it to the third layer. And we do the same for until the fifth convolutional layer. After that, we just take out the output from the fifth convolutional layer and put it into the first refinement layer, and we do the same for the second refinement layer, directly outputting the features outputted from the first refinement layer to the second refinement layer. Now, my model uses a loss function of MSE loss and an optimizer of Adam, which are really good for a convolutional layering model. And we also use a scheduler step LR to make sure that our when our model hits a plateau, we can change the gamma so that our model changes its learning rate and can come out of the plateau. Now, as for what this model can do, we have run this model on a video, and it showed a accuracy of a staggering 98.6%. Now to show you the output, here is the original video, as you can see, and now here is our dehazed video. Now, as you can see, there are more features available here compared to this, and also there are like here you can see the rocks here are very hazed and you can't see the edges of them clearly, but here in our model the edges are clearly visible, and as you can see, you can probably notice this degradation of image. That is not actually degradation, it's the pixel of the video, as we trained it, or as the video is of 256 by 256 size. Thank you, sir.